Okay, so the idea is model computation as a path to a AI and potentially AGI. That's the idea here.
So
So
what is model computation? Yeah.
okay, so first I'll tell why before I go to what is model computation. I'll come to here. Okay, so the idea behind coming up with this idea of model computation is to take inspiration from nature, which is also known as biomimetics. So the thing is that biomimetics means if you want to solve some real world problems, and instead of coming up with a solution with by yourself, the scientists and the engineers they find inspiration from nature. So one example I want to show here is about aquatic robotics. So the thing is that how can we make a robot move efficiently, energy efficiently in an aquatic environment? So instead of coming up with a mechanism on its own, what we can do is, or what the engineers can do is that they can look at real life animals that exist in water and how do they move, because they are because this problem has already been solved by evolution through millions of years of trial and error. So they have found an optimal and energy efficient way to traverse aquatic environments. So here's this example here. So you can see this is a robot, but it moves like a snake,
Mm.
and it's a very energy efficient way. So they have already come up. Snakes have already come up with this. So why try to solve the problem again? Just take the inspiration from the nature. So essentially, this is the idea behind biomimicry, to take inspiration from nature to solve problems. So in the same way, to solve the problem of intelligence. So instead of coming up with mechanisms from the scratch, why not use the techniques that are being used by nature to develop intelligence? So
Mhm.
that's what it is. That's what the model computation. That's what it motivates. It uh, it encourages AI and ML researchers to focus on a naturalistic approach to machine intelligence. So this is the motivation. That's the why behind model computation. I will come to what it is. So what it is that model computation says that the software and the hardware are coupled. So this is what it is. It says that the process that underlie information processing in a biological or an artificial system. So this process is inseparable. That means the hardware, the physical substrate, and the software that runs in the physical substrate, they cannot be divorced from one another. They are coupled. So here's a table that describes the difference between model computation and the traditional computation, which is also known as immodel computation. So here, it is that the software and the hardware are decoupled, and on the model computation, the software and hardware are coupled. So decoupled means that the same software can be run in different hardware. On the other hand, in model computation, what it is that once the hardware on which the software is running, if the hardware dies, the software and everything that it has learned, it goes away too. So that's the main idea. So example, it's very simple. Any biological organism is an example of a model computer, and any software program written in any high-level language for the modern computer. Those are examples of immortal computation. Yes, examples of immortal computation. So the first thing that might come to your mind is that it seems very inefficient, because so far software engineering is coming more and more towards decoupling the hardware and software. So earlier, so if you look at throughout the development of computers and software engineering, earlier programs were written for a specific hardware specific programs were there. So and over time, the attempts have been made to uh, decouple the software and the hardware. So even right now, I'm learning a lot about containers and using Dockers and such kind of things. So even there, it was being said is about the advantage of decoupling. Essentially, they are trying to, in containers, they are trying to decouple the software from hardware as much as possible. Because so what you can do is that you can create a, I think it's called a virtual environment. You can create your own package and everything there. And then you can, through a container, you can implement or you can run that program in any computer. So the software and the hardware are decoupled, and it has a lot of practical advantages from, I think so, from operational point of view. But if you want to develop intelligence from that point of view, there are some drawbacks to immortal computation. So this is what they are trying to say here. That those are the problems that they are trying to solve. So do you have any questions up till now?
I understand some of it partially.
Okay.
The question, like, I cannot frame the question properly because I don't know how to, don't know what the doubt exactly is. But model computation, you're saying where software and hardware are coupled, and
Yes.
if the hardware is not there, the software is also will not be there.
Yes. If for some
Then,
reason the hard. Okay.
yeah.
Continue.
So then, let's say there are some, how should I say? As for example, operating systems
Yes.
for Apple is written for Apple only,
Okay.
and it only supports Apple's hardware.
Okay.
So and there are ways of running that Apple OS in Microsoft or anything else, but that is not the intended goal, or that requires a lot of intervention to
Hmm.
make it compatible. It's almost like a simulation or simulation, I guess.
Okay.
But originally, an Apple operating system will only run in Apple hardware
Okay.
because of the hardware differences and all. So is
Okay.
that also an example of model computation? Because in this case, the software and hardware are coupled to.
I don't think it's completely an example of model computation because uh, as it is mentioned here, software and hardware are coupled. I think by software, in software, we could include two things: instructions and data. From my point of view, it means yes, software would include so both instructions and data. So operating system mostly is instruction, very less data. Data is stored in different. Data is something different. So, and also, if when I move on to the later sections, you'll know that it also talks about other aspects about the separation of the difference in architecture, the von Neumann architecture that's been predominantly used in immortal computation. So that's the reason. I think so. Since memory is not a part of operating system of the computer, I think so. That's why it's not a fully. It doesn't fit the definition of model computation here. So that's my understanding so far. So it might be that it does, but most probably it isn't because, as it says that, thus for us take a biological organism as an example. So for a biological organism, both our, you can say, the operating system and our memory is in our body. So if for some reason we die, so in theory I can say that a traditional computer which is not which doesn't exist in a cloud, which has no connection to cloud, suppose my laptop and all the memory is, if it's stored here, so I think we can call it as a very rudimentary model computer, because if my laptop dies, the operating system is gone, the data is gone, so it's gone. So I think so it's a very rudimentary, a very primitive form of model computer. It could be.
Okay.
So I think that's my understanding so far. Maybe there are a lot of details.
Yeah, I can understand the software and hardware aspect of it, but does it mean that memory will also be erased if the hardware dies? Any part of the hardware dies?
Yes.
Because then it won't be scalable, right?
Yes, it won't be scalable. Yes, talking about those things, I'll talk, when I talk about the architecture, let me come to architecture. Then I think so, it will be much more clearer. So one thing they talk about here in architecture is, okay, I think so through energy efficient. Yes, here I'll talk about the architecture here. So one thing that they say here is that the architecture for a immortal computer is the von Neumann architecture, where there is a separation of the processor and the data. Data and processing is done in different places. Am I correct so far? I forgot the architecture, the von Neumann architecture. Means I forgot the details of the. Do you remember?
Can you repeat again?
Do you remember the von Neumann architecture?
No, how did you describe it? The data and instruction are separate.
Data and memory, instructions and memory are in separate locations. Let me look at it.
I think so. I also don't remember it clearly.
Yeah. Yeah, there is this memory processing. This is the whole. This is the whole of this is processor. This is memory. So memory and processing are separated in von Neumann architecture. That's the underlying idea behind von Neumann architecture. On the other hand, what mortal computation says is that the architecture, what they have proposed is that this won't be separated. Memory and processing will be done in the same place. And they mention it through energy efficiency. I'll talk in this way, and then I'll talk about how it happens. So from an energy point of view, what they say is that there's a thermodynamic cost associated with reading and writing computer memory. So every time the fetching of memory, fetching of data from the memory to the processor, and again sending it back, there's a thermodynamic cost associated with it.
What does it mean, thermodynamic cost?
So means some sort of energy dissipation, some energy associated with it. Energy is required, and there is not just one layer of memory. There's the hard drive, there's the RAM, there's the register, the cache register, and so forth. So there's many levels of many levels of memory, and every time the data pass from one level of memory to the other, there is a thermodynamic cost associated with it. So they mentioned two principles from physics: the Landauer's principle and Jarzynski's equality. So I'll not talk about the details, but the gist of the gist is here is that through these two principles, we can find a lower bound of the thermodynamic work needed. What it means is that there is a lower threshold beyond which you cannot minimize the energy that's required for this transfer. So at least that much amount of energy will be required. You cannot minimize beyond that level. So that's my understanding of it. On the other hand, what they say is that in model compute, so what they also this fetching of memory, this reading and writing process from a computer memory, what they have technically defined there as belief updating. So just think of it as a technical term of reading and writing data from a computer memory. Belief updating. Because in this next statement, I use the same word here. So what they say is that in mortal computer, belief updating is done in memory, which they call it as in-memory processing or processing in memory. And This is done in a certain kind of chip known as the neuromorphic chip. So where these things happen, process happens directly on top of or within memory, thus circumventing the thermodynamic work required in a von Neumann setup. So it is energetically, this architecture is a lot more cheaper as compared to von Neumann architecture. That's the idea that they're trying to say here. So there's a diagram here. Let me see if I can show it to you. Can you see this?
Yeah.
So this is what they have shown here. On the left, they have shown that every time a memory is a data transfer from one level of memory to another memory all the way through the CPU, some amount of energy is expended. This is the architecture. This is the traditional von Neumann architecture. On the other hand, this is what they call it as the neuromorphic chip. So this is the first time I've heard about the neuromorphic chip. So I don't know anything about the architecture or anything. I'm just taking their word for it. Whatever they say, I'm assuming it's correct. So what they say here is that in this architecture, this dissipation of energy at every level, this won't be there because processing will be done in memory itself. So overall, the energy expended will be much less as compared to this one. So that's the first advantage of model computation. But the second one is the central thing. It's about the motivation for developing intelligence. So here I'll talk about two main things: embodiment and activism. So embodiment, this is the same idea that okay. So where does this idea come from? Embodiment. What is embodiment? So what it is that this idea comes from a similar problem in cognitive science. So in cognitive science, there is this question that whether cognition. So what is cognition? It's a broader term for intelligence. Intelligence is a subset of cognition. You can say. So cognition in general, which might also include things like thinking, processing information, and a lot of things. Intelligence, on the other hand, technically defined, is just the ability to solve a problem. If you are given a problem, if you can solve that problem, then you're intelligent with respect to that problem. It's a very narrow definition. Cognition is much more broader. So in cognitive science, there's this question that whether cognition can develop in isolation or cognition is embodied in nature. So isolation says that can an entity develop cognition without a body? On the other hand, embodied cognition, it asserts that the mind is grounded in the details of the sensory motor coupling. So this is a technical term for having a body. That means if you have a body, that means you can sense the environment and you can act upon the environment. So that's the meaning of sensory motor coupling. So what this embodied cognition, what it says is that to develop cognition, body is necessary. You can't just develop cognition out of nowhere. If you have difficulty understanding cognition, just replace it with intelligence. It says that to develop intelligence, you'll need to have a body. Now, because now this body will guide you. So that's the idea of embodiment. So model computation draws inspiration from the idea of embodied cognition. So the authors have taken inspiration from these questions from cognitive science, and they have said yes, to develop intelligence, physical morphology is integral for developing intelligence. Why? I'll try to give some examples. The thing is that your body will motivate you. For example, if you are your body guides what kind of problems you can solve. For example, if you are, suppose I'll give 3 scenarios. Suppose a tiger is chasing you, and suppose you have a body of a human, a body of a bird, or a body of a cat. So based on your body, the problem solving will be done by your brain based on your body. So if a tiger is running towards you and if you have a body of a bird, the solution to this problem as a bird will be to fly away. It won't be, your solution will be to run, because you have the physical apparatus to run, to fly. So that will be the solution. On the other hand, if you are a cat, your instinct will be to climb a tree or something like that. And if you are a human, your instinct will be to run or throw some object towards the tiger. So what solution you come up for a particular problem will depend on what kind of body do you have. So the solutions you are developing. So this is in contrast to the kind of problems that traditional AI solves, because it's just the data is given by, it's trained manually. The whole training process goes through manually, and there is no specific problem. For a specific problem, there are no different solutions based on different kind of computers. It's just one thing. So that's one thing that says that this is one thing that they say. And the whole process behind this, that all of these things will come automatically. There will be no humans in the loop. Everything will happen automatically. And so these are all the details that I have not studied about. So maybe once and I'm done about it, I'll go into the details. But that's the idea behind embodiment. Your body will drive how you solve problems. So your body will drive the development of intelligence. And the second subtopic behind this is enactivism. So when I try to understand what enactivism means, it's actually a little bit difficult to understand. I tried, so I'll just give a very brief understanding, a brief explanation of this topic, because it's a very vast topic in and of itself. It's mentioned here as a part of model computation, but enactivism in and of itself is a very vast topic. So briefly, if I want to explain it, it's about when, again, it's similar to embodiment, but it's a little bit deeper here. So what you say is that the body creates an environment for itself. So far I've said that the intelligence depends on the body, but I also assume that there is an environment out there, and this body is trying to solve the problems that are being presented by the environment to itself. So for example, a tiger is chasing you. So that's a problem that the environment is giving you, and you as a model computer are trying to solve that problem. But enactivism says that you also create your own problems and then try to solve it. So now, for example, initially when I heard this thing, I got confused. What do you mean by creating your own problems? So here's how you can understand it. For example, every human, even though we have the same general thing, but we have our own lives. So for your life, you are solving your own problems. So you are generating your own problems. So for example, you decided to study engineering, but there's some other person who decided to study arts. So you chose your own problem, and now you're coming up with. Did you understand this part? So that's the idea, that you are creating your environment. So even though you can say that, so unlike a traditional machine learning program, suppose, for example, Spotify. Suppose Spotify is a recommending algorithm. So it will do the same thing. If you open in your own app, if you open your app, or if I open my app, it has the same problem. It will just look at your listening history and recommend music based on your listening history. It won't have its own set of goals. But a model computer, in this case, just assume a human. So every human is living their own life, and every human has their own set of problems that they want to solve. But most of the time, we choose our own path and we create our own environments. So even two people living in, suppose you and your colleague living in the same office, you have different problems that you want to solve. So this is enactivism. So So for an outsider, so suppose if I enter your office, I can say, okay, there are two persons in that room, same environment, everything is same. Are the same, but despite everything being same, these two people are solving different problems.
Yeah.
Because they have chosen their own, they have created their own environment in their mind. So objectively the environment is same, but the problems that they're solving within their environment is different. So the problem space is created by the entity itself. So that's the difference. So that's the idea behind it. So the whole idea behind, so far you can understand that the whole idea behind creating this model computer is that to take away human from the training loop. There is no involvement of humans. The computer will interact with the world itself. It will choose its own goal, take data from the environment, process it itself, and so on and so forth. So that's the idea behind it. So that's the idea behind it. That's what they're trying to do here. So that's the overall broader goal of what model computer is. So yeah, that's about it. So maybe in the future when I get into the details, I might talk about it. But this is a broad overview of what the paper is trying to say, the idea behind model computers.
So you talked about one chip, right? Neuromorphic chip or something like that.
Yes,
Does it exist physically? Is there actual production or something like that for that chip?
I think so because I was listening to a podcast on this same topic, from the authors who wrote this paper, and he mentioned about the existence of this thing. Let me see if it exists or not. It's mentioned here somewhere, but maybe it says something about this thing. Brain chip, it's a ultra low power neuromorphic processor. Maybe I think so.
Still a very niche product. I mean niche concept.
Yes, it's a
That
very
is not
niche.
being used. Yeah, in mass.
It's still on the research level. I think so. It's not. There are no actual products or anything built on that. It's just mostly on the research level yet at this moment. So it's a very new topic. So I think so. This paper itself was. Yes, it's not. The dates are not mentioned here, but it's very new. I think so. Not more than a year old. This thing. So it's a very new idea behind this. So any questions or anything else?
Yeah, nothing more. Because this is a very new concept for me, so I don't really have any other question.
Okay. I think so. Okay. Yes, I don't have much to say here too. I think so. It's almost over, but just a few more, just one or two things more. So there's this concept of self-supervised learning here. I think so. It also uses this concept, the things that, and which I'm mentioning here because I want to talk about it in some later videos or something like discussions about there is this thing, self-supervised learning, reinforcement learning with human feedback, and there's another thing.
Unsupervised.
Yes, unsupervised learning, as well as something called representation learning. I think self-supervised learning is one way of implementing representation learning. So these are the things. I think so. Those are actually being implemented in LLMs and whatever the latest AI implementations are going on. I think those concepts those principles or techniques are used there. So I hope to discuss those things in the future as well, not just in context of model computation, but in practical uses in the way that it's used as well. So yes, that's all I have to say. So
Stop for
I
today.
think, yeah, okay.